Hello, everyone. Come on in. We got 4 of you so far. Does anybody have any questions while we're waiting for other people to stagger in? I think that's the first time I actually use a proper word. I keep getting confused when I go to say stagger and I can say straggle or some crap like that. I think I've made up all litany words.
I have a question on the lab, if that's okay.
Okay, go for it, dude.
So on all the previous labs, like on like the same sheet like that you give us to like answer all the questions, you want all the answers on there. But this time we have an actual report. So do you just want the report in a separate file, or do you want it on the back end of the sheet that's posted on Canvas?
No, I just want the actual lab write up. You don't have to turn in the other parts. So
right.
Write it up, make sure you have the graphs and the tables in with the proper units and the calculations in and all that stuff.
All right, cool. That sounds good. Thank you.
No problem. All right, we're up to 8 people in here now. Or 8 people coming. Anybody else have any questions while we're waiting? All right, well, it's time. So, and I got right about half of you, so I guess I should go ahead. We are actually in the process of trying to finish up chapter 14, which then comes chapter 15. Remember, hopefully y'all remembered you had a test due Sunday. You got another one due tonight or tomorrow night. So make sure you get those done. If you didn't get the ones on Sunday done, you need to let me know and I can let you do it late, but there's going to be a point penalty. So just make sure you let me know. I don't want anybody getting zeros on tests, and I shouldn't be giving makeup or late tests, but at least I can take off points if you do it. So that way I've taken off 10 points instead of giving you a 0 is a lot better scenario for me and probably for you. So hopefully no one missed it, but there's always someone, so just in case. It seems like no one has any questions other than the one asked about the lab, so I'm going to go ahead and start rolling into chapter 14.
I do, though.
Yeah, go for it, Tristan.
The chapter 11 homework, is that due this? When is that due?
Yeah, it should be due because we finished it some time ago, as well as 36. Both of those should be due, maybe even already due.
I got 36 done, and I got the conceptual done for 11. I'm behind on the chapter 11.
Well, there's a minor, if you're late, there's a minor deduction per day or something like that. So I'd try to get it done as soon as you can. But yeah, the 11 should be done by now or by tomorrow, I think. I'm not sure what I said of that, but anybody else?
I believe chapter 11 was set for being due last night.
Last night? Oh, that's right, because you are Tuesday, Thursday class. So yeah, that would have been last night. But yeah, remember, there's only a minor penalty for 1 day. So if you do it today, in other words, within 24 hours, you can get a very little bit off, and that's a lot better than a 0. All right, so let's get started. Last time we talked about a simple harmonic oscillator. I talked about Hooke's law. We gave you an example of using Hooke's law to first determine the spring constant, and then to apply that spring constant to determine a subsequent stretching of the spring when you put an additional when you put an additional weight on it. Then I actually gave you a setup for initial conditions for a harmonic oscillator, so you could fill in what the A and the phi were in x equals a cosine omega t plus phi. So that was something that's going to go on and on and on for the rest of the semester, and the rest of this chapter, and the rest of the next chapter, all of the next chapter, in fact. So those are just techniques of using results from differential equations. You're not necessarily expected to know in this class how to solve the differential equations. You're supposed to either know how to solve it and then use what you happen to know how to do, or more, or supposedly the lower hanging fruit, which I always found was not the lower hanging fruit. You just memorize the results, and then you use initial conditions to write the right answer for whatever your differential equation is. So that's why I'm showing you all the details of how to solve these differential equations, because I found it a lot easier to understand how to solve the differential equation. And then by doing it a couple times, I actually remembered the equation itself. So not only did I now have the equations memorized, but I knew how to get them in case I ever forgot them. So in doing so, we have some interesting stuff that we have to do today. So I'm going to introduce you to something that I mentioned before. I told you guys about doing Taylor series and Mclaren series. So now I'm officially making it an extra credit homework assignment to do it. You'll have to put at least 9 non-zero terms for each of the expansions. But if you turn it in, I can give you basically, if we're dropping 2 of the lowest homework grades, now we'll drop 3 lowest from due to that. Okay, so if you do it, that's the way that'll count. So here it is. This is the Mclaren series. The difference being Taylor series would have an A there and a parenthesis x minus A with the I power there. This is just a special case of A being 0. So this is the Mclaren series. And basically it's an expansion around x equals 0. And it says the summation from I equals 0 to infinity is 1 over I factorial times the ith derivative of the function evaluated at 0 times x to the ith power. Now, I'm going to write down the results. I suggested you do sine x. I suggested you do cosine x. I suggested you do e to the x. I also suggested you do parenthesis 1 plus x, close parenthesis to the n power. And I still think that's a good thing for you to do. But these 3 are really essential probably to everything you're going to do in any science or engineering you're going to go to. So I want to go ahead and give you what the answers are. One thing you might remember is that the sine function is what we call an odd function, meaning if you look for the first 2 pi and you compare that to the 2 pi to the left of it, you get upside down images of one another. That's called an odd function. And what that means is the sine of negative x is equal to the negative sine of x. And because of that, you might wonder why they call it odd. Well, now you'll see. It turns out the very first term in sine is theta, or excuse me, in this case it's x. Is x, and then there's a minus. That's actually technically the first term. The 0 term is 0 because the 0th derivative of sine is sine, and then you evaluate sine at 0, you get 0. So the I equals 0 term is 0. So this is actually 1 over 1 factorial x to the 1 minus 1 over 3 factorial x to the 3 plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7 plus 1 over 9 factorial x to the 9 minus 1 over 11 factorial x to the 11 plus dot, dot, dot. So you can see why it's odd. Obviously, all these powers are odd. And of course, if you put -1 in any one of them, you get negative of what you got when you put +1 in there. So you can automatically see that's that. What I'm saying is you're going to have to show me the derivatives and eke out each one of these terms for 9 non-zero terms. So right now I've got 1, 2, 3, 4, 5, 6. So you need to do 3 more non-zero terms. You'll find out that in fact, once you do the 4th, it starts to repeat itself. So it's actually quite easy to get through 9 terms. So don't flip out. Now the cosine is going to seem weird, but it'll fit really nicely with this. But here's the weird part: when you see how this and this are related to this, all of it's going to make a lot more sense, and you'll have a better way of memorizing it. So cosine actually does have the 0 term, and that just gives you 1, but it doesn't have the 2 term. Actually, let me see. Yeah, it doesn't have the 1 term, but it does have the 2 term. So it's going to say minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th. Let me let the student in. minus 1 over 6 factorial x to the 6 plus 1 over 8 factorial x to the 8 minus 1 over 10 factorial x to the 10 plus 1 over 12 factorial x to the 12 minus dot, dot, dot. And remember, cosine is actually an even function. So you'll look, cosine goes like this, and then the left-hand side's its mirror image, and that's even. And you see the even powers, and that of course means cosine of negative x is cosine of x. Okay, don't know why this extra parenthesis is there. That was supposed to be a c. So that's the even function. Now check this out. Once you see the e to the x, it'll all make a lot more sense. E to the x is 1 plus x, which is 0 factorial, 1 over 0 factorial, 1 over 1 factorial, plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th plus 1 over 6 factorial x to the 6th plus dot, dot, dot. Okay, so you can see how these two sort of combine to make that. And the thing that you're seeing is if you were to plug in, for instance, a e to the I theta, you plug in I theta for x, obviously you're going to get 1 here. But here you're going to get I times x. So that's just I times the first term of sine. And then here you're going to get I squared, which is negative 1. So you get negative 1 over 2 factorial x squared. Well, that's that term in cosine. And then here you're going to get I cubed. Well, I times I is negative 1 times I again is negative I. So now you're going to get I times the second term. And if you keep doing that, you'll see that that comes up. And in fact, you get Euler's identity, which says that cosine theta plus I sine theta is actually equal to e to the I theta. And the other version, e to the negative theta, is equal to cosine theta minus I sine theta. Okay. So all of this stuff is super, super cool, super, super valuable, super, super important. And in fact, we're getting ready to use this one in a second. So as I said, do first 9 non-zero terms of all 3 for extra credit. Okay. All right. With that being said, let us begin. So I'm going to now tell you that it turns out not only does the mass on the spring give you the same differential equation that we call the simple harmonic oscillator. In fact, remember the simple harmonic oscillator was d2x over dt squared plus some constant, which in our case was k over m, times x is equal to 0. So anytime you have a second order derivative of x and then x over here with some constant in front of it and all that equal to 0, then you automatically get to know that x is equal to a cosine omega t plus phi, and that a and phi are determined from your initial conditions, but omega is going to be the square root of k over m, and of course f is going to be 1 over 2 pi times the square root of m over k, or excuse me, k over m. And that t, which is 1 over the period, is going to be 2 pi times the square root of m over k. These are all things that you automatically have anytime you find a differential equation like that. No matter what the constant is, even if there's a constant out in front, you can divide the whole equation by that constant, and it'll just make a different constant here, and that constant is what goes under the square root. So every time you find that, that's great. Well, let's look at some examples. First off, I'm going to take a simple pendulum. So here's a simple pendulum. And initially, it doesn't look so simple. So let me show you what I mean by that. So here's a simple pendulum hanging from a ceiling. by a massless string of length L. And it's really not massless, just long as the mass is, you know, a factor of 100 smaller than the mass of the ball, then everything's great, right? And let's say it's out at some angle theta. Then it turns out there's a force acting on it, mg this way. Of course, there's a tension acting along this way. But you can break down this weight into a component that's parallel or anti-parallel to the tension, and then a component that's perpendicular to the tension in the string, and that was mg sine theta. So we could solve this with Newton's second law, or I can do it with Newton's second law in torque form. I'm going to do it with Newton's second law in torque form because I like it. So the summation of the torques is equal to I times d2 theta over dt squared. Okay, now you're looking as the whole system is the string plus ball. And in fact, we know that a ball orbiting in a circle, say, about a point with a radius of orbit L is just ml squared is the moment of inertia. So that's what's going in there. Torque, on the other hand, remember torque, one of the ways we did it was we said the component of R perpendicular to F, and then the other one we did it was the component of F perpendicular to R. Well, I know this is the component of F perpendicular to R, and in fact, I know that theta going up means the force is going to be pointing in the opposite direction, so I have to use a negative on there. So that's going to give me negative. Now the torque is this force times this lever arm. So I'm going to say negative mgl sine theta is equal to, notice that's torque because I got the L in there, is equal to ml squared d2 theta over dt squared. I'll divide both sides by ml squared. Okay, and get them all on the same side. And when I do that, I'll get d2 theta over dt squared plus g over L sine theta is equal to 0. So that's not quite it because I don't have just a theta there. If I had a theta there, then this would be like the constant, and this theta would be theta here, which matches this being with that. So it would be the nice differential equation that we like. But here's the kicker. Let's say theta is a really small angle in radians. Let's say theta is 0.1. That's 1/10, right? So if I put 0.1, which is close to 0, and therefore this Taylor series expansion, Mclaren series expansion should work, then I get 0.1 for this first term. The second term is going to be 0.1 times 0.1 times 0.1. That's 1/1000th. And then divided by 6. So it's going to be 1 over 6,000. So 0.1 is way, 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 way bigger than 1 over 6,000. And because of that, we know this term is fairly negligible compared to that one. This is going to be even worse. This is going to be 1 over 5 times 4 times 3 times 2. That's 20, 60, 120. That's 1 over 120 times 100,000 in the bottom. So 120 times 100,000 in the bottom. That term's going to be huge, hugely small as well. I know that's sort of a oxymoron, but you get what I'm saying. So really, in the small angle approximation, and that's what it's called, the small angle approximation, sine theta is approximately equal to theta in radians is really the way that's supposed to be measured. But still, with that in mind, it helps you. And in fact, your book points out that even at 15 degrees, sine theta in radians at 15 degrees differs from theta in radians at 15 degrees by about 1%. So you can tell it's not that bad. In fact, when we do our lab in class, where we're actually hanging a mass from a string, I've actually pulled this up to 60 degrees and calculated the period formula that we get from the differential equation for the small angle and compared that to the actual period, and don't get more off than by more than 2 or 3% at most. So you can tell you can go pretty high and still be cool, at least in terms of the period. So with that in mind, now I have d2 theta over dt squared plus g over L, which I should write lowercase l since I did that, times theta is equal to 0. So that's exactly the form. So we now can say theta equals, since we learned that A is really the maximum amplitude, we can just call this theta max if we want, cosine omega t plus phi. And we even know that omega is equal to the square root of g over L. Of course, F would be 1 over 2 pi times the square root of g over L, and t would be 2 pi times the square root of L over g. Okay, so those are all new things that we have, new toolboxes or new tools in our toolbox for solving physics problems. We don't have to go back and solve the differential equation. We just know that it's held, or that the laws of physics say it's going to obey this differential equation. So these answers must work for it. So let's look, for instance, at an example, and hopefully I can find the example that I made before. And I may or may not be able to, but that'll be awesome. Okay, yeah, so here you go. Let's say some geologist goes out. So this is example 1. Some geologist uses a 26.43, I'm going to go ahead and label that L just to make it simple, 43 centimeter simple pendulum near a site on Earth, and finds its period to be, or excuse me, its frequency to be F is equal to 0.9705 hertz. What is G? Okay, so this is a way in principle that a geologist might go out and try to find, say, let's say you're looking for uranium. Uranium's super dense, okay? So if you got a big deposit of uranium directly under you, you've got a little bit more mass per cubic meter directly below you than other spots on the Earth. Therefore, you'd expect gravity to be a little bit stronger there. Therefore, if you take a pendulum and determine G, and G happens to be really big, then maybe it's because there's uranium under you. If it happens to be low, maybe it's because there's water under you or something less dense, even more so than water. But the main thing is you can detect the changes in G from the period of a pendulum, and those changes in G can tell geologists neat stuff. So let's look at our solution for this. So the solution just requires us to remember that this is a simple harmonic oscillator that solves a differential equation. And that differential equation has this solution, and it has this angular frequency, and it has this frequency, and it has this period. So since we were given the frequency, I'm going to say frequency is equal to 1 over 2 pi times the square root of G over L. And that should apply, right? We're just assuming that he kept it out of gusty wind and stuff like that, because the air resistance could cause a problem. Now, if I rejigger that a little bit by writing 2 pi F is equal to square root of G over L, then I can square both sides and I'll see that 2 pi F quantity squared times L is just equal to G. And that's what I'm going to do. So G is going to be equal to 2 times pi times 0.9705 hertz. Now, just for the record, remember we say omega is equal to 2 pi F. What that really is doing is basically converting the F, which is in cycles per second, it's converting those cycles to radians per second, because there's 2 pi radians every cycle, and this is cycles per second. So you get radians per second for omega. So that's what's going on here. This 2 pi is changing these cycles to radians. So I'm also ultimately on this side going to get radians per second. And then, of course, I'm going to square it because that's what my algebraic formula says. And then I'm going to multiply it by 0.2643 meters. And now I have meters per second squared, which is exactly the unit of G. Now, when I do that, I get 9 point, and you should verify this because I just did 2 problems in a row with my class and I inadvertently flipped my equation upside down and got the wrong answer. So make sure y'all verify this. I got 9.8276. I'm using 4 sig figs and everything. So really this is an extra sig fig, and that's meters per second every second, or you could just call it meters per second squared. Of course, I could go on with this problem. I could go back and say, okay, well, what's the actual period of the pendulum, or what's the actual angular frequency of the period? Okay, well, what's the equation of the period if, equation of the angle that the pendulum goes through if it's initially at rest, but has a initial position of theta equals, 0.5 radians.
Professor?
Yes.
So the hertz and the frequency is the real kicker here. Like if you did another planet, the hertz would be completely different.
Yeah. So for instance, if the G went up, you can see that the hertz would be higher. If the G went down, the hertz would be smaller. Of course, you can also affect it by different lengths of pendulums and stuff like that as well.
I feel like that'd be small effect because that would also affect the hertz also.
Yeah. In actuality, if you look at the formula, they affect it equally because G and L are both proportional to square root of the frequency.
Okay, cool.
So, but inversely, so larger G means larger frequency, larger L means lower frequency. You can see this too. There's a park, Chesapeake Playground or Chesapeake Public Park right off of Volvo Parkway. They have one swing that's got like 20-foot long chains. And it's really cool because normally, your chains are 8, maybe 10-foot long on a swing set, but on a swing set with 20-foot long chains, man, you get a really, really long period, short frequency, but long period. So it's a kind of a neat little swing experience. But anyways, it's fun when they do stuff like physics in the playground. So anybody have any questions on that? Well, the next problem we're going to solve has a similar scenario going on. In this case, it's going to be what we call the physical pendulum. So a physical pendulum is a pendulum that oscillates, but it has sort of a random shape, if you will. So this is the physical pendulum. Okay, so let's imagine for a second that you've got some random shape. And it's pivoting about that point. And let's say your center of mass is this point. Okay, let's say it has a mass M, and let's say it has a moment of inertia I. This distance from here to here is H. And remember, this is your pivot point. So I'll put a little circle on it like that. And in fact, this angle right here is theta. Again, we have the summation of the torques is equal to I times d2 theta over dt squared. So the torque in this case, just like last time, it's going to be H times mg times sine of theta. But again, it's restorative, so it'll be a negative m I used a big M, so I should stick to a big M here. Big M G8 sine theta is equal to I times d2 theta over dt squared. Dividing both sides by I get d2 theta over dt squared is equal or plus mgh over I times the sine of theta equals 0. But again, I make the small angle approximation. So in that case, sine theta goes to theta. So I get the simple harmonic oscillator equation again. And lo and behold, I get for this one, theta is equal to theta max times cosine omega t plus phi again, where omega in this case is going to be the square root of m times g times h over I. And frequency is going to be 1 over 2 pi times the square root of m g h over I. And t is going to be 2 pi times the square root of I over m g h. Okay. So we've got a whole litany of equations again that we can use, all because of the small angle approximation. So we see pendulums, at least in the small angles, behave just like the simple harmonic oscillator. So does the physical pendulum. So life is really good. So let's examine another physical problem using this new result. Okay, so I'm going to pull this page out. You can keep it nearby so we can still see the results that we're wanting to use. So this will be example 2. I see y'all cannot see that, so let me pull this down a little bit. Okay, so this is going to be example 2. Okay, it appears I have misplaced my example 2, but I can make it a new. This one didn't really have numbers anyway, so it wasn't a big deal. So example 2, a cylinder. I'm going to assume uniform. A cylinder of mass m and radius r is hanging and oscillating as shown. Okay. What are omega, f, and t? So here's the drawing. I'm going to have a cylinder that's supposed to be, you know, like a perfect circle basically, and it's supposed to be uniform. Wow, that's a pretty good circle. I'm impressed with that one. I don't look too bad. We got a little bulbous here, but anyways, what I'm going to do is I'm going to imagine it's oscillating about that point, and I'm going to say the center of mass is right here, and this distance is going to be 7/8 r, and of course this distance is r. Similarly, this angle right here is theta. So again, I get my same differential equation. It's just a physical pendulum. But here's the kicker. I, in this case, the I for a cylinder about its center of mass, I derived that for you. So you guys should know how to derive that. That's 1/2 mr squared. But that's when it's rotated about the center of mass, the axis of symmetry, right? In this case, is actually rotating about a parallel axis. So according to the parallel axis theorem, that's going to mean that the I about the parallel axis is equal to 1/2 mr squared plus m times the distance between the center of mass and the point about which it's rotating is 7/8 r. So I'm going to put 7/8 r and that whole quantity squared. This, of course, becomes 32/64. That's what 1/2 is. This becomes 49/64. And then both of that's times mr squared. So 32 plus 49 is really nice because that happens to be 81. So I get 81/64, which is 2 perfect squares. And that just makes me so excited I can't even explain myself. Okay. Now we can make use of what we learned earlier. What we learned earlier was how the omegas are related to these quantities. So I can now say omega is equal to the square root of mgh over I. So it's m times g times 7/8 r over 81/64 mr squared. Well, that's, kind of a crap show, if you will. One of these r's will cancel out and the m's will cancel out, but all I'm left with is a g in the top and an r in the bottom. So I'm going to have the square root of 64 times 7 over 81 times 8 times g over r. Well, this is going to be 9. The square root of 81 is 9. The square root of 8 is 2√2. So I'm going to say omega is equal to, basically, that'll be 9 times 2. So that'd be 18. And this is the square root of 64 is 8. So I'll be 8/18 the square root of 7 over 7g over 2r. I can simplify that, and when I do so, this 8 does not go into that, but the 2 does, and the 2 would leave a 4 up here and a 9 down here. So this is 4/9 square root 7g over 2r. So that's the omega. Obviously, the worst part of that was just the algebra, or the arithmetic, excuse me. Now f is just 1/2 pi times this. Well, the 1/2 pi, that 2 is going to cancel out with this 4, leave a 2 up here. So I'm going to say 2/9 pi square root 7g over 2r is going to be my f. And of course, I can just flip that over to get my t. So my t is just going to be 9 pi over 2 times the square root of 2r over g.
Wouldn't it be 7g in the bottom?
Oh, thank you. Yes, it would be. I don't know where that 7 just went. Stupid. So yes, you're right. Thank you. I'll box that off. So any questions on that? That makes pretty good sense, right? But you can see now, I mean, the only thing that's left really to do this, if I wanted to make it even more exciting, is I could give you some initial conditions so you can determine the theta max and the phi. But I've showed you how to do that, so there's really no additional value in me showing it to you, just from you seeing it. So just make sure you consider that. But that's about all there is left to do these types of problems. Now, there's 2 more sections left in this chapter that I do cover. And well, there's one section I do cover and the other section I don't cover. But I do expect you sort of to do the homework with it because it's just a straight plug and chug formula thing. So the first part is the damped harmonic oscillator, and I'm getting ready to work that. And the other part is the forced damped harmonic oscillator, and your textbook author just gives you the answer, right? Once you take a differential equations class, you'll see how this is attacked. I'm going to attack it like you do in a differential equation class because the way he does it, he goes ahead and says the solution I know should be some exponentially decaying cosine function. So he puts like e to the negative gamma t times cosine omega t plus phi, and maybe puts an amplitude out in front of it. But you can see by having a e to the negative gamma t times the cosine omega t plus phi, that's a product of functions. So to plug it back into the differential equation, you're going to take the first derivative of a product, using the product rule, in other words, and then you're going to take a second derivative of the resulting products. So it's just a mess. It's a lot of algebra. It's in some sense simpler because you're not doing anything fancy from differential equations, but in some sense it's way harder. So I'm going to just do the damped harmonic oscillator the way I like to do it, and you'll learn something that will come in handy when you take differential equations if you haven't already. So damped harmonic oscillator. Now you can actually make this a spring hanging downward in case the force would be like mg or something like that, but it doesn't have to be that. It could have been you pulling it or whatever. The main thing is you're going to have a spring and you're going to have a force negative kx acting on that. Remember, it's a restorative force, so if your x is positive, the force is going to be in the negative direction. If your x is negative, your force is going to be in the positive direction. And it's going to have another thing that is the damping part. And this is really a coefficient of friction, basically, or excuse me, a coefficient of air resistance. So it's some b times the velocity. That, again, is always going to be the opposite direction of the velocity. So you put a negative behind it. Those are the two forces acting on the mass. And then according to Newton's second law, since the mass isn't going to be changing, we can use the MA version. So that's going to be m d2x over dt squared. So what I get is d2x over dt squared plus b over m times dx over dt plus k over m times x is equal to 0. So that's the differential equation for a damped harmonic oscillator. Notice the only addition is it's got a middle term with a constant times the derivative. Notice the x's are still the same thing. With respect to time, still the same thing, a constant in front of it. You can still have another constant in front of this, and it'd still be the damped harmonic oscillator problem. It's also called a linear ordinary second order homogeneous. That means it's equal to 0.
What is B again?
That is the coefficient of air resistance, basically, and it'll have units of like Newton seconds per meter.
Do we ignore that normally in our equations?
Yeah, you do. This time we're actually taking it into account. And the neat thing is this same equation with different numbers in front of it turns out to define how an LRC circuit behaves. So inductor, resistance, and capacitance obeys the exact same equation, even though it has nothing to do with wind and springs and stuff. So the homogeneous just means it's 0. When we add a force to it, a forced damped harmonic oscillator, that would just be like some force over here. It could be a constant, it could be a cosine function, it could be a sine function, all sorts of stuff. But again, your textbook author just gives you a equation that is the right answer for that, and you just apply it blindly like we've been doing in the past. So what I'm going to do is I'm going to tell you that this has a solution. And I'm going to make use of that fact that I told you about e to the I theta being cosine theta plus I sine theta. I'm going to make use of that. And I think you can see by the nature of this, looking at this equation, if you have a function x whose derivative is proportional to the original x, you're going to always find a solution, right? Like if you took the derivative of e to the x, you just get e to the x. So if you take second derivative, you're still going to get an e to the x, still going to get a c e to the x, still going to get an e to the x, and you get that characteristic equation like we had before when I said, you know, rho squared minus k over m is equal to 0. But now it's going to be an actual quadratic equation. So let's do this. Let's say this is our on-site solution, which is a guess. Let x equals sum a times e to the rho t. Then the first derivative of x with respect to time is just going to be rho a e to the rho t. And I wrote it that way so you can see it really is just a number times the derivative. It's an eigenfunction is another way of thinking about it. If you think of the derivative as an operator, this operator operates on the function and spits out a constant rho. Now I can take the second derivative, and again, I'm going to get a rho squared a e to the rho t. So now I can plug all these in. I'll get rho squared a e to the rho t plus b over m times rho a e to the rho t. That's for that term. And then for this term, I just get plus k over m times a e to the rho t is equal to 0. And this is really Newton's second law. So when I do this, rho squared plus b over m rho plus k over m times a e to the rho t, I know this must be true for all time. Because of that, this is not going to allow it to be 0 for any time in particular. So this can't be making what's making it 0. It must be this characteristic equation that's making it 0. So you can tell that's a quadratic equation, and you can immediately see that rho is equal to negative b over m. Remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. So negative b over m plus or minus the square root of b over m squared minus 4 times 1 times k over m. All that divided by 2 times a, which again is 1. Now I'm going to separate this and make it two separate fractions. So I'm going to get negative b over 2m plus or minus. Now I'm going to take a big square root, because what I'm going to do is I'm going to suck this 2 in the denominator inside the square root. In order for you to have something inside the square root and it pop off as a 2 in the denominator, that thing in the square root would have had to have been a 4 in the denominator. So a 2 outside is the same thing as a 4 inside. So I'm going to now say b over 2m. That whole quantity squared makes that 2 a 4. So that's why I did that. And then minus, remember you had 4k over m. Well, that 2 squared inside is going to cancel out that 4. So I just get k over m here. Okay. So I think you can tell this gives us potentially 3 different answers. So there's 3 scenarios here. Okay, the 3 scenarios are b over 2m squared is greater than k over m. That's one of the possible ways we can do it. Notice if that's the case, then you get a square root of a positive number and everything works just fine. I'm looking for something I'd written earlier to make this part a little easier for you guys. Maybe I stuck it over here. Yes, that's what I did. Okay, cool. So in this case, what's going to happen, because in order for an exponential, e to the rho t, in order for that to give a sine or a cosine, we have to remember that e to the I theta is equal to cosine theta plus I sine theta, right? So in order for us to get a cosine, the real part of this imaginary part we can ignore all day long, but in order for us to get something sinusoidal, we have to have an e to the I power. If this is actually a positive under the square root, we're not going to get any I, so it's not going to oscillate. In fact, it's going to turn out that you're going to have basically two exponentials added to each other. And this is called overdamping. And an example of overdamping, I can give you, where did I just write that? I know I wrote it somewhere, darn it, it's making me mad. Crap. I got all my thoughts together, had this wonderful thing written out so you guys could see it crystal clear. And I stuck it somewhere, and I don't know where I stuck it. Crap. Oh, well, I worked out B's, K's, and M's really nicely, so you could get ones that you could take to Desmos and graph. But I don't know what happened to that right now. But unless I find it in the next 2 minutes, you ain't gonna get to see it, and that's kind of stinky. That's not it. That's not it. That's not it. That's not it. Oh well. So I get rid of those. Get rid of those. This is okay. Okay, so I think I could possibly still work it out from here. So one example of overdamping would be when B over 2M squared is actually equal to, or is actually greater than K over M. So my example for that turned out to be, I said B squared over 4M squared is greater than K. Okay, I said B equals 5. And that's Newton seconds per meter. And I said M equals 3 kilograms. And I said K is equal to 2 newtons per meter. That's a case of this, okay? Another case is, so I'll call this A. Another case is K over M being greater than B over 2M squared, in which case you will get oscillation. And oddly enough, that's called underdamped. Okay, this one's actually going to be something along the lines of a e to the negative gamma t times a sine or a cosine or something like that. So in this case, you actually get a cosine function or a sine function times e to the negative gamma t. And I think the B I chose for that was B equals 3, M equals 3, and K equals 2, I want to say. I really should make that M equal 3 a lot bigger than that. Notice the M and the K, the M didn't change. Okay, so let's double check, make sure that's right. B would be 3 over 2 times M would be 2 times 3 would be 6. So it's 3 over 6. That's 1/2. 1/2 squared is 1/4. 2 over 3 is 2/3. So yeah, 2/3 is bigger than 1/4. So this is definitely the case. And like I said, what you're going to get is a e to the negative gamma t cosine blah blah blah. Okay. And then the final one, C. Now this is a weird thing. In this case, you have B over 2M is equal to K over M. Actually, B over 2M squared is equal to K over M. And this one, you get no oscillation either. And it's called critically damped. And the reason why is this one turns out to be something like A1 plus A2T times e to the negative gamma t. Okay, and I'm just using a constant in there because that's what your book used, but that's what theta ends up becoming in this case. So it's literally a linear function times exponential decay. The reason why it has to happen is it turns out, notice when the b over 2m squared is equal to k over m, that part's 0. Well, this is a second order differential equation. You have to have two functions, or at least two variables that you can tweak with the initial conditions. And this only gave me one. So it turns out from the theorem, from basically the learnings of what we've learned from differential equations, that when you have this type of differential equation, the linear harmonic oscillator type, damped harmonic oscillator type equation, you can take the one solution that did survive, which is the e to the negative b over 2m, and multiply it by a linear function. And in fact, if the power of the function, or the order of the function that's linear like this, is say n, then you only have to go up to an n order polynomial. So for instance, if you got one solution, then you'd need up to a1 plus a2t plus a3t squared plus a4t to the fourth, so on and so forth, until you got an t to the n power times that. So that's the way that's supposed to work. And those are the scenarios. It's critically damped. So you see only one of those come out. Now, that's the physics behind it, and that's really the parts you need to know. What is overdamping, what is underdamping, what is critically damped. Now let me show you what it means. Okay, so or you can do the Desmos yourself using these values. Oh, and by the way, I do have a value for B's and all that in the critically damped case, which is what we were just talking about. So a critically damped case for this one would be B equals 3. Again, that's 3 Newton seconds per meter. M equals 3 kilograms. And then, of course, you'd have K. In this case, has to be something weird. It turns out to be 8/12, which is 2/3. So if you use 2/3 newtons per meter, you'll get B over 2m squared is equal to K over m. Okay, so you can plot these ultimate functions that I give you now in Desmos. So we've got 20 minutes, so let me show you what we're going to do. So let's take case A. And A is supposed to be overdamping. So what happens in overdamping? Well, what we have is, since we have two different solutions because of this plus or minus, the way we fix that is we say, okay, well, in this case, the equation was x. So I'll say x is equal to a1 times e to the negative b over 2m plus the square root of that god-awful mess, all that times t. Okay. And then I have the other one, so I have to add that as a linear combination. That's what we learn in differential equations. Basically, you can have, you need two constants, and if you got two different functions, put one constant with one function and another constant with the other function. The only thing is there's like certain tests, like the functions have to be linearly independent, which you'll learn about, but it's really a plus exponent and a minus exponent is more than enough. And in this case, we're going to get a e to the negative b over 2m minus square root, and then all that times t. So that's actually what the solution is. But notice the square root in this case, since b over 2m squared is greater than k over m, there's not going to be an I because the square root is just a normal number. Okay, it's not an I. So with that in mind, we can sort of settle out what the initial conditions are. You could say x of 0, meaning x at time 0, is equal to some amplitude a, and you could say the derivative at time 0 is 0. So if I want to do that, let's say first off, dx dt is equal to a1 times negative b over 2m minus square root times e to the negative b over 2m minus square root times t. plus A2 times negative B over 2M minus, or this one would be, that one would be plus square root, this one would be minus square root, times e to the negative b over 2m minus square root, all that times t again. So that's our derivative. If we say x of 0 is just equal to some amplitude a, what that means is I plug in 0 here. So this is e to the 0, which just becomes 1. This is e to the 0, which just becomes 1. So I get a is equal to a1 plus a2. And then when I say v of 0 is equal to 0, then that tells me 0 meters per second is equal to, and this I could say a meters, for instance, but 0 meters per second is equal to negative b over 2m plus square root times a1, and then plus negative b over 2m minus square root times a1. So all that's supposed to be equal to 0. I think what you can, minus a2, sorry. This is supposed to be a2. So I think what you can see is these two have to add up to give you 0. And you can, of course, solve for a1 in terms of a2 and then plug it back in here, and that'll get you everything you need. Let's go ahead and do that. So I will say b over 2m minus square root, all that times a1, that's me flipping this to the side. So it changed signs. That became a positive. This became a negative, is equal to negative b over 2m minus the square root times a2. So I can say a1 is equal to negative b over 2m minus square root over negative, or over b, sorry, over 2m plus, no, that's minus square root again. And again, remember that square root is just this junk. So it's not anything fancy. It's just avoiding writing all the stuff. So this is b over 2m times a2. So that's one expression expressing a1 in terms of a2. So a is supposed to be something I know. I can now plug that version of a1 in here, and I'll have a, something I know, with a2, something I don't know. So I can just solve for a2. So I plug all that in. I will get a is equal to negative b over 2m minus square root over b over 2m plus square, or minus square root again. Times a2 plus a2. Well, you can clearly factor the a2 out, and you'll get a is equal to, getting a common denominator will be b over 2m minus square root, and then plus negative b over 2m minus square root, all that over b over 2m minus square root times a2. So what you can see happens here is the b over 2m and the minus b over 2m cancel each other out, and I get negative 2 times the square root. So a2 is going to be equal to b over 2m minus the square root over 2 times the square root, and that should be negative. So I can actually make that negative by doing this plus and this negative, and all that will be times a. So now I have a2 in terms of a, and I have a1 in terms of a2. So in principle, I can go ahead and say that a1 is equal to this holy mess, negative b over 2m minus square root over b over 2m minus square root times this holy mess, which is negative b over 2m plus square root over 2 square root times a. So now I have an expression for both A1 and A2. So I've basically solved for the two unknown variables, A1 and A2, all in terms of A, which, you know, might be 4 meters, for instance. And it's a lot easier if you're actually using numbers, which is why I put the numbers in the first place. But I noticed I kept making some arithmetic errors when I was doing the numbers. And I might still have an algebra error in here. God, I hope not, but I might. Okay. So now we've got all that stuff. And that's really wonderful. We've got some actual answers. So I can actually write out what the function is now. So it turns out x, for those initial conditions, x of t is equal to, now let's compute what b over 2m is. I said for this case, b was 5, m was 3, and k was 2. So first off, A1, b was 5, m was 3, so 5 over 2 times 3, that's 5, 6. So that's negative 5 over 6 minus the square root. Now b over 2m, again, should be 5 over 6. And 5 over 6, of course, squared is 25 over 36. And then k over m, of course, k is 2 and m is 3, so that's 2/3. So 2 over 3 is that. Of course, 2/3 of 3/6 is actually 24. So you can see that actually 25 over 26 minus 24 over 36 is pretty good. Now I can make that over, again, positive 5/6 minus the square root 25/36 minus 2/3, like that. And then now I got this thing. So this is negative 5 over 6 plus the square root 25/36 minus 2/3. All those square roots are going to become a lot simpler in a second. And then over 2 times the square root 25/36 minus 2/3. And then all that times A, which I'm going to say A is 4 meters. So let A equal 4.00 meters. And then that means this is 4.00 meters. And that's all just A1. So let's simplify this a little bit. 36 minus, again, I multiply this by 3 over 3, or excuse me, by 6 over 6. 6 times, no, not 6 over 6, 12. So 12 times 3 is 36. 12 times 2 is 24. 25 minus 24 is 1. The square root of 136 is just 1/6. So we've got negative 5/6. Negative 5/6 minus 1/6 over 5/6 minus 1/6. Negative 5/6 plus 1/6, and 2 times 1/6. Okay. And then that is all times, of course, e to the whatever, but that's just for us getting what A1 is. So maybe I shouldn't try to write the function first. Let's go ahead and make this just plain A1. Just to make it a little easier. So now that I got ability to do A1, I'm going to say A1 is going to be negative 5/6 minus 1/6. That's negative 6/6, which is, of course, negative 1 over 5/6 minus 1/6 would be 4/6. And then times negative 5/6 plus 1/6 would be negative 4/6. And then 2/6 down here. So you can see this 4/6 is going to cancel out with that 4/6. And you can see the negative times the negative is a positive. That's just 1. So this is going to be 6 over 2, or just 3. 3 times 4 is 12, equals 12.00 meters is A1. Okay. Now A2, which is actually a lot easier to do, A2 is negative B over 2m plus square root over 2 square root, again, hoping I didn't make any mistakes, times 4.00 meters. And this gives me negative 5/6 plus 1/6 over 2 times 1/6 times 4.00 meters. Negative 5/6 plus 1/6 would be negative 4/6 over 2/6 times 4.00 meters. Obviously, this 6 and this 6 is going to cancel out. This 4, negative 4 divided by 2 is going to be negative 2. Negative 2 times 4 is negative 8. So say negative 8.00 meters. Hopefully, I did all my arithmetic correctly. Now I
It's
can
that
go.
simple.
What's that?
It's that simple.
Yeah, it's that simple. But believe it or not, that's supposed to be, you know, arithmetic stuff. So that's supposed to quote unquote be easy. But remember, our original hypothesis was that x is equal to a to all that crap, a times e to all that crap plus a2 times e to all that crap. So now I can just write out that x of t is equal to 12.00 meters times e to the negative. B over 2m is a whole different scenario, but we found that it's 5/6 t. And then we also found times e to the positive square root, which was 1/6. So that's 1/6 t. So you could left it as negative 5/4 plus 1/6 if you wanted, or you could just write it like this. Well, normally we write it like this because this one will be the sine function, or excuse me, this one will give us a sine function or a cosine function. But in this case, I'll say negative 5/6 plus, we had negative 5/6 plus 1/6. So negative 5/6 plus 1/6 is negative 4/6 t. And you can see that's just an exponential decay function. Now the other one is negative 8.00 meters. And then e, in this case, it's negative 5/6 minus 1/6. So that's negative 6/6. So that's negative t. So that's the whole function. Now, what I would normally do if I hadn't used up so much time doing all this basic arithmetic is I would first go back and make sure that the 12 and the 8 work out fine for the boundary conditions. Like 12 plus negative 8 really does equal 4. So that makes me feel a little more confident about my math. But does 12 and negative 8 give me 0 here? Well, this one is negative 5/6 plus 1/6. That's negative 4/6. So negative 4/6 times 12 would be negative 48/6. And this one gives me negative 6/6. So that's just negative 1. And this would be negative 1 times 12. So 48 times 12 times 6 be negative 40. Yeah, that actually adds up. Okay, so it looks like I did it right. But this is the function, and you can see it's just exponentially decaying. So in fact, it should just look sort of like this. Well, actually never cross the axis because it can't get to 0. So that's what overdamped looks like. Now, we've only got a couple more minutes, but the good news is the rest of it's actually a lot easier now that we've sort of worked out the details. Part B is the underdamped. So in that case, we end up getting x is equal to a1 times e. Now, in this case, I said use b equals 3 and m equals 3. So b over 2m would be 3 over 2 times 3, which would be 3 over 6 or 1/2. So this would be negative 1/2 t times e. Now, remember, since k over m is bigger, that's going to give us a negative under the square root. So I'm going to now say I times, now I have the square root of, in this case, b over 2m is going to be 1/2. So when I square it, it's going to be 1/4. And then 1/4 minus 2/3. So it'd be 2/3 minus 1/4. 2/3 minus 1/4. That's going to be, multiply this by 4. That'd be 8/12 minus 3/12. So that's the square root of 5 over 12. So I root 5 over 12, which you could actually reduce that, but I'm not worried about it that way. And then it'll be plus a2 times e to the negative 1/2 t e to the negative I 5/12 t. So I'm not going to do the boundary conditions for you on this one. You've seen how we do it, but here's what you do, and then you can just throw away part of it. It's really amazing. So I get x of t is equal to, let's just pull the e to the negative 1/2 t out in front. And I'm going to say it's a1 times just the cosine of root 5 over 12 times t plus a2 times the cosine of root 5 over 12 times t. The reason why is this is a negative. Remember, e to the I theta is cosine theta plus I sine theta, and e to the negative I theta is cosine theta again, plus negative I sine theta. We're throwing out the i's because that's imaginary, and that's our whole thing. And you can see a1 plus a2 is just going to be the same as a new constant a3 because they're both multiplied by cosine 15/2. Now you can see this is actually going to give us a function that is sinusoidal, or in this case, cosinusoidal. So it'll look like this. In other words, the e to the negative 1/2 t is acting like an asymptote, and that's the underdamped. Finally, the very last part, we're actually we're technically out of time. Let me do this one little part, and that is the critically damped. The critically damped is b over 2m squared is equal to k over m. So you end up just getting rho is equal to negative b over 2m. Well, that's not good enough. And the fundamental ideas of differential equations say that in this type of differential equation, you can just multiply it by a polynomial. So we'll say x of t, in this case, is going to be a1 plus a2t, all that times e to the negative b over 2m t. I gave you a value for b over 2m. It's 3, 3, and 2/3 for k. So I'm going to say this is now a1 plus a2 t times e to the negative b, which was 3 over 2m. That's 3 over 6. So that's again negative 1/2 t. But you can see that's just a linear, you can see that's just a linear function multiplied by an exponential. And with this one, you would normally get like this. That's an exponent. I mean, that's a linear equation. But in this case, it's going to go like that. So it almost looks like the first case. So that's the entirety of the damped harmonic oscillator. I know when I went through this course, I didn't get that only one of these even had a trig function in it. So hopefully I've at least explained that well enough for you guys to make sense of. So that was really my goal in showing you all these exciting details. If anybody wants to take the time and use these B, K, and M values that I have, and do that same initial condition, x of 0 equals, say, a, which is 4 meters, and x dot, or the velocity at 0, is equal to 0, and then do the initial conditions and graph these in Desmos, I could probably find some extra credit for you for that too. So you guys are free to go. If you have any questions, stick around. Otherwise,
Yes.
I will see you next time.
Thank you.
Thank you.
Thank you.
Thank you again.
I have a question.
Yes, go for it.
So this is just going to follow the same principles that are in differential equations when we solve two second order differential equations with three possible outcomes with the same roots, being that it's e to the power of the root plus e to the power to the root times x. And then if they're same and if they're different, it's going to be e to the r1 and e to the r2.
Mhm.
Of course, there's two separate constants that separate them within addition.
Yep.
And then there's the third one that uses cosine and sine based off of the beta and the alpha that you find from the when you do the quadratic equation for it.
Right.
This is what it all boils down to.
Yep. It's exact same as they teach in virtually every ordinary differential equations class.
Yeah, when
So
I had my test, I had to actually even draw it up like the map, like you did, like you drew up the chart of what it looked like.
Oh, good.
Oscillating. So
Yeah, it's really hard to parse the difference between the overdamped and the critically damped unless you play with Desmos or using your calculator's graphing function. It's hard to
yeah,
see
we had
the
to do
difference in
that.
them. Yeah, that's cool. Well,
right,
hopefully this
Professor.
helps your differential equations knowledge a little bit better. And the one thing I think that's best about a physics class after DiffEQs is you finally see, oh, wow, okay, so DiffEQs really are important.
Yeah, I got the spring stuff back in differential equations. I just had a really hard time with Bernoulli's principle. I still don't really
Yeah,
understand
that's
it.
always some tricky algebra to get it in the right form. But then when you get it in the right form, it has that nice little quote unquote easy solution. I like the
Yeah,
exact differential equations. Those were kind of the funnest ones for me. That and the infinite sums. If you put in infinite sums and start taking derivatives and then set
yeah,
the
that get kind of fun.
yeah,
But
it's,
if
it's
you,
like a little puzzle,
I,
like linearizing or diagonalizing a matrix or something.
all right, Professor, thank you.
All right, no problem. See you, Tristan.